Let me welcome the next speaker, last but one speaker in our afternoon session, and this time we shall listen to Analytic torsion of 235 geometries by Stefan Haller.
Thank you for the introduction. Let me start by thanking the organizers for the opportunity to give a talk here. And here's a brief outline of my talk. I'm going to begin by explaining what this analytic torsion of 235 geometries actually is. Then I will present a particular example where we can compute this analytic torsion. And in the third part of the talk, I will reinterpret this calculation and express the result in terms of zeta functions, which have a more classical flavor. So as many of you know, a 235 geometry is just a 5-manifold together with a rank 2 subbundle in the tangent bundle, which is bracket generating and has a growth vector of 235. So that means sections of the Lie brackets of sections of this rank 2 bundle generate a rank 3 subbundle in the tangent bundle, and if you take triple brackets, that is going to span all of the tangent bundle. So this turns the manifold M into a filtered manifold, and the non-trivial filtration subbundles have ranks 2 and 3. The associated gradient of the tangent bundle becomes a bundle of nilpotent Lie groups. The fibers are called osculating algebras or symbol algebras in this community rather. In this case, the symbol algebras are all isomorphic to a particular 5-dimensional graded nilpotent Lie algebra with 2 generators, x1 and x2 in degree -1, and brackets as indicated here. Let me give a few examples. We can, of course, take the simply connected Lie group corresponding to the symbol algebra. It's a 5-dimensional Lie group. And on this Lie group, we have invariant 235 geometries. Another example or class of example arises when we take two surfaces and the one surface is rolling on the other one without slipping and twisting. That gives you a 5-dimensional configuration space, and this non-slipping and twisting condition can be encoded in a rank 2 subbundle. And if the Gaussian curvatures of these two surfaces are disjoint, then this is going to be a 235 geometry. These are some examples. Equivalently, these geometries can be described as parabolic geometries of a particular type, namely of type G2P, G2 the exceptional Lie group, and P a particular parabolic subgroup. From this perspective, the most basic example would be the homogeneous space G2 mod P, which is diffeomorphic to S2 cross S3, or at least its universal covering. But the geometry is locally diffeomorphic to the simply connected Lie group I mentioned before. This point of view will not play an important role in my talk. Associated with this filtered manifold comes a Romain complex, and that can be understood as a special case of a BGG complex, namely the BGG complex associated with the trivial representation, but we will not make use of this. So there's a Romain complex, and the Romain complex associated to such a manifold is a complex of differential operators, which is naturally associated to the geometry and computes the Rahm cohomology. We will twist this complex with a flat vector bundle F to extract more interesting topological information. Twist it with a flat vector bundle F, and then we obtain a complex of differential operators which computes the Rahm cohomology in the coefficients F. The operators, the Romain differentials here, are differential operators of higher order. In particular, or more explicitly, the Heisenberg orders of these Romain differentials are 1, 3, 2, 3, and 1, as indicated in red underneath the arrows. The Romain differential takes sections of the bundle EQ to sections of a bundle EQ plus 1. And what is this bundle EQ? Is just a fiber-wise Lie algebra cohomology of the osculating algebras, the simple algebras, twisted with this flat vector bundle F we're considering. The ranks of the fiber-wise Lie algebra cohomology is 1, 2, 3, 3, 2, and 1, so it's considerably smaller than the Rahm complex, which would have ranks 1, 5, 10, 10, 5, and 1. So what would we like to do? So here's a complex that computes the round cohomology. What we would like to do is we would like to compare the analytic torsion of this Romain complex to the analytic torsion of the de Rham complex. The analytic torsion of the de Rham complex is the Ray-Singer torsion. That's a classical object that's well studied. In particular, it has been shown to essentially coincide with the Reidemeister torsion, which is a topological invariant. So we would like to study an analytic torsion of this Romain complex and then compare it with the Ray-Singer torsion. To define an analytic torsion, to do analysis with this complex, we need formal adjoints of the Romain differentials. And in order to get formal adjoints, we pick up a sub-Riemannian metric on the rank 2 bundle, and we choose a Hermitian fiberwise metric on the flat bundle we're twisting with. And then we get standard L2 inner products on the space of sections of these bundles EQ. And that gives rise to formal adjoints of the Romain differentials. And they are, of course, going to be differential operators again. And then we would like to look at the zeta function associated with these Romain differentials. So we would like to look at the zeta function that we take the operator d star d, raise it to the power minus s, and take the trace, and hope for the best. These operators d star d will have, for q different from 0, they will have an infinite dimensional kernel, but the remaining part of the spectrum consists of isolated eigenvalues with finite multiplicities only. And these eigenvalues will all be real, because it's formally adjoint, and positive. So you can write the zeta function also in terms of the spectrum as indicated on the right-hand side. And of course, the big question is whether this series converges. And you can indeed show, and this is where they work, one actually has to work. One can show that for sufficiently large S, real part of S sufficiently large, the sum here actually converges and defines a holomorphic function. This holomorphic function can be extended to the entire complex plane, and it's going to be holomorphic at 0. This analysis has been worked out in collaboration with Shantanu Dave, and his name should be on this slide, definitely. I forgot that. The reason why this works is because the Romain complex is a Rockland complex in a Heisenberg calculus that's adapted to the filtration. And therefore, it has analytic properties very similar to elliptic complexes. And everything I said here about the zeta function is classical in the elliptic setting, also has been worked out in the Heisenberg calculus on contact manifolds, but we can do that on any filtered manifold. Yeah, and then once we have the zeta function at 0, we take zeta prime at 0, and this is going to be the regularized determinant of the operator. This is the usual way of zeta regularizing operators. You take zeta prime at 0, because if you differentiate the definition of the zeta function, at least formally, at s equals 0, you get log of the determinant. But now it has a rigorous meaning, because we actually have the derivative of zeta at 0 at our hand. And the analytic torsion of the complex is just the alternating product of these determinants. So with the logarithm is going to be the alternating sum of zeta prime at 0 in each degree. So this is our definition of the analytic torsion of the Romain complex, and it should be thought of as a graded determinant of the Riemann complex in a zeta regularized sense. And yeah, we would like to compute this spectral invariant and in particular compared to the Ray-Singer torsion. So the analysis I mentioned here has been worked out quite generally, and we can define an analytic torsion for every Rockland complex over a filtered manifold with very weak assumptions on the filtration. So what keeps me from considering more general filtered manifolds at this point? Why do I stick to 2, 3, 5 geometries? The reason is that the Romain complex is a Rockland complex only in a graded sense on general filtered manifolds. In order for our analysis to work, we need a Rockland complex in the strong sense. And the Romain complex is only going to be a Rockland complex in the strong sense if the osculating algebras, the simple algebras, have pure cohomology. Pure cohomology means that the grading automorphism acts as a scalar in each cohomology group of the simple algebra. Here are some types of filtered manifolds with this property. Trivially filtered manifolds, of course, have this property. Then the Romain complex is just the Ram complex, and this gives rise to the Raysinger torsion. Contact manifolds have this property. In this case, the simple algebra is a Heisenberg algebra. And you get the Romain complex that is associated to contact manifolds, and that leads to the Romain-Sichard torsion, which has recently been studied. And then there are 2, 3, 5 geometries where this happens. And of course, I was looking for further filtered manifolds with this property, and I could not find any. So here's a question: are there any further graded nilpotent Lie algebras with pure cohomology? If a graded nilpotent Lie algebra has pure cohomology, then then you can look at the grading automorphism in cohomology and take the graded trace. And that can, of course, be rewritten as this product on the right-hand side. And notice that the product on the right-hand side doesn't depend on the Lie algebra structure, but only depends on the dimensions of the grading components. And if it has pure cohomology, then this polynomial has to have precisely dimension of g plus 1 non-trivial coefficients. And that turns out to be an extremely strong restriction. And you can rule out many possible gradings in low dimensions, rule them out and show this way, by just considering this polynomial here, show that they cannot have a Lie algebra structure with a pure cohomology. I actually used some computer algebra system to scan a range of possible dimensions here, and I could not find anything else. Anything else than listed above, except for, of course, you can change the grading in a trivial manner. Consider contact filtration concentrated in degrees 2 and 4, 3 and 6. That works, but I could not find anything else. So this is yet another very peculiar phenomenon about the 2, 3, 5 geometries. Okay, so now we have on our analytic torsion, we can associate to this Romain complex, and let me talk a little bit about its basic properties. Again, the notation is up here. The torsion depends on our manifold and the DST distribution, the rank 2 subbundle. Capital F, that was the flat bundle we're twisting with, and then we had to pick up like a Subramani metric G and a Hermitian metric on the flat bundle. It's going to be additive in F. If you take the analytic torsion of a direct sum of 2 flat bundles, you just get the product. This is not surprising. This is what it's supposed to be. That works, and it's trivial. It's also compatible with Poincare duality. If you compute the analytic torsion with respect to the dual bundle, you get the same as with the original bundle. And it has good behavior with respect to finite cover rings of 2, 3, 5 geometries. So everything here is really rather straightforward. The first result we have concerns the dependence on the metric we picked up. If we change the metric, the analytic torsion will depend on the metric. How does it depend on the metric? And we can show that the infinitesimal variation of this analytic torsion with respect to the metric can be computed locally, in the sense that from the local geometric data, you can produce a density, and if you integrate the density, then you get the infinitesimal variation with respect to the metric. The same is true for infinitesimal variation with respect to the Hermitian metric on the flat bundle we had to pick up. And the same is also true with respect to infinitesimal variation of the rank 2 subbundle. And that already does a deformation of the rank 2 subbundle can change the geometry dramatically, as you all aware of. But nevertheless, the torsion will only change by a local quantity. The interesting dependence of the torsion is the dependence on the flat bundle F and the dependence on the homotopy type of the rank 2 subbundle. So this is work in progress, but I'm virtually certain, but it yet has to be written up. There should be a universal natural polynomial formula that expresses this local quantity alpha in terms of the curvature of a connection, the torsion of this connection, its covariant derivatives, the metric, the covariant derivatives of the metric, and so on. But that yet have to write that up. Okay, so let's turn to a particular example where we can do a computation. Let's consider nil manifolds. So we look at this 5-dimensional nilpotent Lie group, simply connected. I denote it by G. We look at the right invariant 235 geometry on this nilpotent Lie group G. We take a right invariant sub-Riemannian metric. So we get a 235 geometry on the nil manifold G mod the lattice. We pick up a lattice in this nilpotent Lie group, denoted by gamma, and we look at the nil manifold G mod gamma. And on G mod gamma, we have a 235 geometry. We also take a unitary representation of the lattice, because that will induce a flat vector bundle over the nil manifold, and that comes with a Hermitian metric on its fibers. So we have all the data for the analytic torsion to be defined. And the first thing you observe in this situation, that the analytic torsion does not depend on the right invariant sub-Riemannian metric, and it does not depend on the right invariant 235 geometry we are using. The reason for this is that any two right invariant sub-Riemannian metrics can be connected by a straight arc of right invariant sub-Riemannian metrics. And any two right invariant 235 geometries, distributions, can be connected by an arc of 235 geometries which are right invariant. So during this deformation, you never leave the regime of right invariant geometries. And this permits us to compute this local quantity in the theorem I mentioned before, and it turns out to be 0. So the infinitesimal variation is 0, and therefore the quantity doesn't change. So this is where the analysis enters again. And now we would like to compare it with the Reysinger torsion. The Reysinger torsion is defined in terms of a Riemannian metric, but it's well known that on odd-dimensional manifolds, the Reysinger torsion does not depend on the Riemannian metric. And so the natural object to consider is a relative torsion, the comparison between the torsion I've just introduced and the Reysinger torsion in the denominator. We expect that this is 1. I definitely conjecture that this is 1. I can only show a partial result towards this direction. In general, I would expect that the comparison with the Reysinger torsion for any 235 geometry with the of this torsion with the Reysinger torsion should be computable in terms of a local quantity, but this is still in its infancy. Okay, so here's the theorem I mentioned, the partial result we have. We fix the lattice gamma, and we can show that the analytic torsion is locally constant in the representation rho, as long as we restrict to one-dimensional representations rho. So it's locally constant in rho. This is the theorem I would like to present. I emphasized locally in red because if I could do a little more and prove that it's actually constant for each gamma, then it would follow immediately that the constant has to be 1, and then the relative torsion would be 1, even for arbitrary unitary representations rho. So this is okay. Let me sketch the key ideas in the proof here. We notice first that a one-dimensional representation of the lattice gamma, of course, factors through the abelization. The abelization is an extension of C2 by a finite abelian group. In this case, you just look a little bit at the lattices in this Lie group. So the space of representations, the dual group, is just U1 cross U1 times a finite abelian group. So the space of one-dimensional representation consists of a finite collection of tori. And the statement up there is, on each of these connected components, the analytic torsion is constant. But we do not know the relation between the different components. That's what the theorem tells us. And how do we prove that? We look at symmetries. We look at automorphisms of the Lie group G, graded or not, any automorphism that preserves the lattice gamma. And such an automorphism will induce a diffeomorphism on the nil manifold, G mod gamma, and it will act on the representation rho. And by naturality, this relative torsion remains unchanged if we act on the row with such an automorphism. So the relative torsion is going to be constant along the orbits of these automorphisms. And it turns out that this group of automorphisms is rather large. Any automorphism that preserves the lattice will induce an automorphism of C2. So this is going to give you an element in GL2 of C. And one can show by analyzing lattices in this particular Lie group that the image of the automorphisms in GL2C is a subgroup of finite index. And then there's a well-known fact, GL2C, when acting on R2, has dense orbits. So GL2C acting on U1 cross U1 will have dense orbits too. And the upshot is that we can cover this space of one-dimensional representations with finitely many orbit closures under the group of automorphisms preserving the lattice. And a little last piece of analysis tells you that this relative torsion will depend continuously on rho. Actually, it's going to be smooth in rho. So this relative torsion is constant along the orbits. By continuity is constant along the orbit closures, but our space is covered with finitely many orbit closures, and then it follows that it's locally constant. So this is the reasoning here. Let me now translate this computation, or the result of these computations, in more elementary terms. And what we're going to do is we take the Roumain complex on this nil manifold. On the nil manifold, the group G acts, and we are going to decompose the Roumain complex into irreducible G representations. So Kirillov described all irreducible unitary representation of nilpotent Lie groups, and then bijective correspondence with coadjuvant orbits. And for this group, it can be worked out explicitly what all irreducible unitary representations of G are. For any two numbers, alpha and beta, there is a one-dimensional representation where x1 and x2, the generators of the symbol algebra, just act by multiplication by alpha and beta, essentially, and everything else acts trivially. These are precisely the representations that factor through the abelization of the Lie group G. Then for every non-trivial real number h, there is a representation on L2 of R. Here x1 acts by differentiation, x2 acts by multiplication with x, and x3 acts by the commutator, which is just a scalar. So this is the familiar Schrödinger representation of the Heisenberg algebra. And in fact, these are precisely the representations that factor through the center and actually come from a three-dimensional Heisenberg group. And then the bulk of representations can be parameterized by three parameters, lambda, mu, and nu. Real parameters, the representation space is again L2 of R. And x1 and x2 now act by a combination of differentiation and multiplication with a quadratic potential, a quadratic polynomial. x3 acts by multiplication with x, and x4 and x5 are central, they act by multiplication with scalars. So this you can explicitly describe all irreducible unitary representations of this group G, just following Kirillov's parameterization. Let's look at the Roumain complex, what the Roumain complex looks in these representations. And for simplicity, I will only consider the operator d0 star d0. So this, on the nil manifold, this is a sublaplacian that just differentiates into the directions of the rank 2 bundle. And in the representations, well, in the one-dimensional representation, it's just multiplication with the scalar. That's not very interesting. But in the Schrödinger representations, that will give you a harmonic oscillator. And in the representations associated with the representations of the third kind, this is going to be an oscillator with a quartic potential, a quartic oscillator. It should not say harmonic here. I'm sorry, it's a type. So it's a quartic potential here. So this is what d0 star d0 looks in these representations. d1 star d1 would be similar, but it now would be like matrices. That would be a 2 cross 2 matrix of operators with a similar flavor, but higher order now, 6th order, the polynomials and the differentiation. Yeah, and what we're going to do now is we are going to decompose the space of, well, the sections of our flat bundle over the nil manifold is a module under the G action, and that can be decomposed into irreducible components. And Richardson worked out exactly which representations appear and with what multiplicity. And here is the result you get when you follow his arguments. For simplicity, I restrict at a particular lattice here. At this point, I take a lattice that's generated by just two elements. That has the effect that the abelization has no finite abelian part. And so representation rho of the lattice is then just characterized by two real numbers a and b, mod integers. And the decomposition of the sections of the flat bundle over the nil manifold into irreducible G representations looks like that. You have some of these one-dimensional representations appearing. The parameters alpha and beta must be integral up to a shift determined by the representation rho. Then you have some of these Schrödinger representations appearing, but only for integral h, with multiplicity though. And then you have some of the other representations appearing, of course. The numbers lambda, mu, and nu have to be integral. So lambda, mu have to be integral. Nu has to be integral up to a shift again. And they will appear with multiplicities. And the multiplicities apparently look like interesting number theoretic functions. The condition here is the multiplicity is just the number of residues k mod d, such that k times k plus d is congruent to n mod 2d. So that is very close to the condition n is a quadratic residue mod 2d, but not quite. But it has a very number theoretic flavor, the multiplicities that appear here. These multiplicities might be zero, by the way. They're not all non-trivial. So you can work out explicitly what the decomposition looks like. And the zeta function will decompose accordingly. Get a contribution from each representation. So I wrote down the zeta function again. This zeta function, zeta prime at 0 is the analytic torsion, alternating product. By Poincare duality, you can actually express it in terms of the first three Riemann differentials, because the third and the fourth by Poincare duality just give the same contribution like the first and the second. So you can rewrite it in this way if you want to. Does not help much though. It's shorter. And then the zeta function will decompose just like the representation decomposes. We have some contributions from the one-dimensional representations. This can be virtually certain that this can be like worked out explicitly what that gives you. You should be able to express the first sum here in terms of classical Hurwitz zeta functions. The contributions from the Schrödinger representations, the middle sum, will be related to the Riemann zeta function. In particular, the contribution from d naught star d naught. This is the harmonic oscillator. We know the spectrum of the harmonic oscillator explicitly. If you look at the zeta function, it's just the Riemann zeta function. And then you can work out this sum here too. So the contribution for the middle sum, at least the one coming from d naught star d naught, can be worked out explicitly and is related to the zeta function associated with the harmonic oscillator. And the contribution from the right hand, from the sum on the right hand side is more involved. That now involves the spectrum of the quartic oscillator. We do not know the spectrum of the quartic oscillator explicitly. We do not know the zeta function of the quartic oscillator explicitly. Only few values of this zeta function have been computed explicitly by Voaros, I have seen. And so even for the third sum, even the contribution from the d naught star d naught is already quite complicated, quite involved. But nevertheless, what does our theorem, our result, our computation tell us? It tells us that zeta prime at 0 does not depend on the parameters a and b. So this sum of zeta functions, if you compute a zeta prime at 0, it's going to be independent of a and b, and conjecturally it should be 0 for all a and b. integral. So that gives a relation between classical Hurwitz zeta functions associated with the harmonic oscillator, and zeta function associated with the quartic oscillator. So this is a way of reformulating the statement that the analytic torsion is locally constant in rho. This is locally constant in A and B. Okay, so this is what I wanted to say. I thank you for your attention.
So thank you very much, Stefan. Questions, comments? Nice lecture, nice timing. Question, dear.
The condition that you had on I don't know how you phrased it, that the cohomology is pure. This corresponds to the fact that in each step of the Riemann complex, all the operators have the same order.
Have the same Heisenberg order, precisely, yes. Yeah, so if you take the adjoint, so the analysis comes from, the results come from analyzing like a Hodge type of Laplacian. You take d star and d star d, but the right kind of power, so these have the same order, and then you add them, and then you get a Rockland operator that has good analytic properties. That's where everything comes from. But taking d star d and d star, in order to get a Rockland operator, you need that the Heisenberg orders are pure. Otherwise, the standard L2 inner products are not the right concept. Otherwise, you would have to use Sobolev inner products to compute the adjoints. Then everything gets way more complicated. In particular, we cannot do the heat trace asymptotics. We don't have the zeta function extension. The analysis gets way more complicated.
Thanks. Some more questions, comments? Seems not to be the case. So let me thank Stefan again.